But now I want to make sure that Otis Walton gets his full time.
This, on the right-hand side, my name's Otis Walton. I'm going to talk about some scaling laws relating to scaling gravity and scaling particle size and how that affects granular flow. And all of this stuff is well known, but not necessarily well known by people who are new to looking at things on the moon. And on the right-hand side, I just show two examples. One is a numerical example with a discrete element model of flow out of a hopper under terrestrial gravity, exact same materials, exact same conditions, just change it to lunar gravity and the cohesive material doesn't flow. The picture down below is JSC1A flowing out of, that's about a 6-inch diameter PVC pipe with and then it had a flat bottom on it. We had about an 1.25-inch hole in the bottom, and it would flow kind of intermittently. And this is a snapshot during a video of the JSC1A on the left-hand side flowing. We made a low G simulant. What we did is we took the JSC1A, sifted out all of the coarse material, 70 or 50 micron and above, and replaced it with 70 micron glass bubbles. It had a density 0.12. So we lowered the rho GH. We lowered the density of the regolith by a factor of 6. But we kept all of the fines from the JSC1A, so it had all the same cohesive properties. And then we tried to let that flow out of the same opening, and it just formed a little arch and wouldn't move. We banged on the side, and we could get a stable rat hole. We banged on the side again, and this is after about the second or third time we banged on the side of it, and we could get stable arches. But it just goes to show this was our cheap way of doing a KC-135 flight. We just changed the density of the regolith instead. But it was a way of doing it. Next slide, please. And I can't tell if I don't have a video or not, because I can't tell if the next slide is up. I will assume it is up for you.
The slide change has happened. I'll work on that. If it doesn't, I'll fill it in.
It's up now, and I can see it. I guess my video is now back. That's good to know. This is a review of interparticle cohesion effects. Let's see. I guess I could start video as well. There's no reason about having my video. It did come on. Yeah, so you can actually see me. There was something that was mentioned today when Dave Carrier showed the vertical wall that Harrison Schmidt had made, and he attributed that to cohesion. And in reality, because I'm going to be talking about interparticle cohesion effects in handling and processing, but not drilling and excavating. In drilling and excavating, you have an additional effect, which is the critical state soil mechanics people would call it shear dilatant effects. And that was what contributes to forming the vertical wall. Cohesion contributes a little bit to that, but most of it is because the soil is over-consolidated. So those vertical walls, and the reason the drill holes are stable is because the in-situ regolith is over-consolidated. It's way denser than what's called the critical state. If you have it lower at the critical state or lower, then it would only cohesion would hold it up. But it's much more than cohesion that leads to those vertical walls being able to be a meter high or so and not collapse. It's the over-consolidation. If you talk to a soil mechanics expert, they can give you more details on critical state soil theory. But a short summary of what I'm going to talk about today, a little review of bins and hoppers. And the bottom line is, if you go to the moon and you have 1/6 gravity, you need to have openings that are 6 times larger if you want to get it to flow reliably. Rotating equipment, we have scaling rules. And the scaling rule, if you have rotating equipment like a rotating drum or a screw auger or something like that, you want the acceleration of the centrifugal acceleration at the periphery divided by gravity to be about the same as it is on Earth to get the same mode of flow. Fluidized beds, we find that the particle boundaries between where you can have cohesive behavior or arable behavior shift to larger particles. So under lunar gravity, you have to have well, the finer particles don't fluidize well. And I'll talk a little bit more about tribocharging as we go on. Why don't we go to the next slide? On Earth, when we talk about interparticle cohesion, most of the time we're talking about surface tension from liquid bridges, from adsorbed water. And on the moon, that's not an effect that we are concerned about. So the first bullet item on the slide I'm assuming your slide is up, is not something that we care about. Electrostatic forces, you've heard quite a bit about in other talks today, and that is something we care about. Electrostatic forces will attract particles to surfaces. If you have a tribocharged spot or even just a solar wind or photoelectric charged material, it will adhere to a conducting surface. The regolith is generally not conducting. If you bring that next to a conductor, it forms an image charge in the conductor and it sticks. The easiest example of that is take a balloon, rub it on your hair, put it against a stainless steel refrigerator door, it sticks. The balloon is non-conducting, it gets a charge. The charge that touches the metal surface goes away, but the charge that's near it isn't. And so all charged regolith will stick to conductors. Doesn't matter if the conductors are grounded or not. It's going to stick to the conductor. The van der Waals forces are present. As soon as you have electrostatics bringing things together, you have then a combination of electrostatic charge and van der Waals forces acting to hold it together. And the combination of those two produce a pull-off force. And instead of the picture I have at the bottom, I should have had a discussion of what's called the bond number, and that's the ratio of the pull-off force to the weight of a particle. And that's the important characteristic that determines whether a granular material will behave cohesively or not, is what that bond number is. If that bond number gets to be greater than 5 or 10, you start seeing very cohesive effects in the powder. And I'll talk a little bit more about that. But van der Waals force goes linearly with the particle size. The bond number goes inversely with the particle size. So if we take the ratio of the van der Waals force to the weight, we find that it increases with the inverse square of the particle. So as particles get smaller, the bond number goes up very dramatically.
Right, I'm going to
Next slide.
turn my video on when you have 2 minutes remaining. So you actually have 1 minute remaining at this point. So I'll do this for everybody.
I'm having trouble even understanding your audio. I'm sorry. My internet connection is terrible.
You have 1 minute remaining.
Are you able to understand my audio?
You have 1 minute remaining.
I'm sorry, what? Okay.
1 minute.
Then I will get to the bottom line. Let me skip this one. Just say go to the next slide. There's theory for hop bins and hoppers that has been verified. Glenn had JSC1A tested. Turns out you need about a 6 centimeter opening. If you then take that exact same theory, go to the next slide after yeah, that's fine. Leave it there. If you go to low gravity, instead of being 6 centimeters, it's 30 centimeter opening. That means that hopper openings that are smaller than a foot in diameter are probably going to require some kind of flow assistance. So there are ways that you can get around doing that, but that is not an easy way of handling it. Let's see. I think let's skip the next slide, and so go to the next slide, and then skip it and go to the one with the 2 rows of rotating drums on it. And I assume that's up. I can't see it. If we
so you're out of time. We're now over. So if you can wrap up,
tests,
that would be great.
So again, my audio is terrible. Are you telling me I'm out of time?
Yes.
Okay. The final slide was just the same as the original one. It says that and the 3 important things were that bins and hoppers need to be much larger. Rotating equipment, we know how to scale it. Fluidized beds, you have to have, you can use, the solution for fluidized beds is to use a rotating fluidized bed, and that gets you around it. And I will leave it at that and apologize for taking so long to get through it.